Okay. And we've got our, well, just briefly to repeat, this is our, not a lot, I mean, assignments, so there's probably a number of things we might talk about there. And then chapter 18, there's a lot of stuff to talk about there. So we'll just leave it at that. Okay, so if I go to not announcements but assignments, you can see that there's a new assignment called Counting Binary Search Trees. And right. So let me just introduce that topic with some drawings, maybe. Would that work? Can I do that? I've got paint. Oh, I got to go over here. And if I go to there, I see that I've got this. Does that, I think that's, yeah, so that's a drawing space. It's kind of a funny color, huh? Can I change the color? Something darker, perhaps? Oh, now it's, I think I need to say okay. All right, and then, oh, now I see nothing. I'm not sure why. How about, yeah, okay, so if it's light I can see it. All right, how about if it's more blue? Okay, all right, that works, I guess. So you got a list of numbers, like, can I write them down here? 08, 4, 2, these are different one-digit numbers, okay? 7, and let's say 9, okay? So the way the binary search tree is going to work is you've got an empty tree. That's the starting position, right? You get an 8, right? So you put that as the root because it's first. So the first number is always going to be the root of your tree. Oh, sorry, that's not, how about if I put it up here? Okay, so there's 8, my root, right? Then I get a 4. Well, 4 is less than 8, so I'm going to put it over here. And 2 is also less than 8, and it's also less than 4, so it goes here. 7 is less than 8, but it's bigger than 4, so it goes here. And 9 is bigger than 8, so it goes here. All right? And now, so what we want to do is make that a data structure where the elements are pointers to nodes. So each node contains 2 node pointers. Well, each node contains a value and 2 node pointers, a left and a right. And if there's nothing to the left and nothing to the right, then you get null pointers, which I'm using the null set symbol here to represent the null pointer, but the null pointer is just it's kind of a fake pointer. Is that a reasonable way of saying that? Because it's not really a memory address. It's essentially the number 0, right? Which you might argue is a memory address, but it's not one that we can access. It's not one that can be dereferenced. In fact, dereferencing the null pointer is a common source of undefined behavior that we should maybe experiment with a little bit. But right, so now the question is, and we can't see all of this tree now because I've drawn off to the right, but that's another null pointer to the right of the right child of 9. And so the question is, how many other trees produce that? How many other sequences produce that same tree? Now it's got to be an 8 as the first one, right? Oh, this is now not visible. How about if I do it here? So the first one has to be an 8, right? Because that's the root. But then the next one could be a 9 or a 4. You're going to get the same result either way, right? So currently it's a 4. Let's make it a 9. All right, so now we have a different sequence that produces that same 8 on the root and 9 to its right child. Now the next one has got to be a 4, right? Because there's no other things you can put on the right, and we've got to have this here to the left, so I'm going to have to put a 4 here. Now I've got a choice, right? I can get either a 2 or a 7. So yeah. So there's a weird way in which these are related to the Catalan numbers. Did I just let the cat out of the bag? Out of the bag. They got a cat in the back. No, it's in a bag. Yeah. Forget I ever said anything about the Catalan numbers. And don't think of an elephant. Okay, so now 894 will produce that same thing, right? But then after the 4, do I have a choice? Do I have to put a 2? No, I could put a 7, right? 2 or a 7. So, right, because if I put it, so far what have I got? I got the root and its left and right child, right? Children. So let's go ahead and put the 7 first. Then I have to put a 2, right? In fact, I'm done now, right? There's only 5 numbers here, right? So is there another sequence? Well, yeah, right? The 9 can be in any of these positions after the 8, right? So we could have 8, 4, 9, 7, 2, and 8, 4, 7, 9, 2. Sorry for my bad handwriting. I've got 3 slates here, none of which work properly. One is missing software or a product key, which is locked away in some room somewhere. And I've got an Elmo. What's wrong with the Elmo? Oh, it's a Bluetooth thing. Never mind. Anyway, so I'm writing with my mouse still. Can't be helped. Right, so the 9, we've got now the 9 at the end. We got the 9 just before the end, the 9 in the middle, and the 9 right after the 8. But then you can also sort of rearrange the 2 and the 7. Right, doesn't matter which one comes first. So there is a way of thinking about this as, I don't know, can we think about it as paired parentheses? Maybe. Certainly that's one of the ways of thinking of the Catalan. Oh, there it is again, the cat in the bag, out of the bag. And I'm not quite sure how to describe that other than what I've already said. So let's go to the assignment. Let's see, who do we, oh, we got everybody's here now. Wu is here. I've got not sure who I didn't mention before who's now here. Is it Mario? I think Mario and Mark were here early. Oh yeah, maybe it's Logan. Probably Juan. Okay, fair enough. Okay, so what have we got? I need to unmanaged participants. All right. So Yeah, so I'm just going to, well, I need to put the focus over here and then delete. Okay, so yeah, so now if we go to here and click on here, oops, now I've done it. And I go back, yeah. If I click on here, what happens? It says, oh, what do you want to do? I'd like to open it with, no, I'd like to open it with not Microsoft Edge, but other. Namely, I don't know, I can open with Firefox, can I? There it is. And then it should open in this window. Okay. So it looks like only 3 pages here. Oh, well, that's not so bad. So there's a little background theory about binary search trees, and we've kind of already talked about that. And so here's a case where there's 5. Oh, now here we have some repeated values, right? So with our 5, how many did we see? There was 4 places to put the 9, and then a couple of places to put the... Should we do it again? What was it? It was 8, 9, 4, 7, 2, I think. So again, 5 values, just like here there's 5 values, right? But we also had 8, 4, 9, 7, 2, that's a 7, and 8. It's got to be 8 first, right? So you don't have any choices there. 4, 7, 9, 2, and 8. I'm just going to write right over this here. 4, 7, 2, 9. All right. So that's, you know, with the 4, 7, 2 all in the same order, and the 9 going in any one of those 4 positions. So there's 4 of those. Now for the 8, 9, 4, 7, 2, the 4 has got to appear there, but I think the 2 and the 7 can swap, right? So here you're going to have 8, 9, 4, 2, 7. So if the 9 is in the second position, there's 2 possible ways of doing that. I think that's going to be the same for the rest of these, right? So suppose the 9 is in the third position. Again, we can swap the 7, 2 and go like that, right? And 8, 4, 2, 9, 7, right? Again, we're just swapping the 2 and the 7. And 8, 4, 2, 7, 9. Now, is that all of them? There's 8 of them here, huh? So this is if we have all different numbers, and there's 5 numbers, and you know it's the tree produced by this sequence. Then these other 7 sequences also produce that same tree, using the insertion rule of, you know, go to the left or go to the right and look for the first empty place. Any questions about all that? Do you think there's another one of these? Did I miss one? The 8, 9, and 4 have got to appear before. Let me think about that. Yeah, the 4 has got to appear before the 2 and the 7, right? If you had 8, 2, then, you know, that 2 would be in. Oh, you can't read that, huh? Have I gone off the side again? I'm afraid I have. It's barely visible there, huh? Yeah. All right. Well, I'm just going to grab. I think that's it, right? So there's 8 of them that way, and there's. But now, if you have repeated values, as we do here, then there's only 3, right? So we have 2 3s and 2 4s. So instead of having 8 possible, well, there's also the issue of what is the actual tree, right? So we could make different trees with these same. So the question is, for a given tree, how many sequences make that same tree? That's the final question in this assignment. There's a bunch of little questions leading up to that, which is how to build the data structure for the assignment. Why is there a D here? I don't know. I don't remember that D. That's D is for delete me. All right. All right. So start by creating a node object in a header file, bst.h, with the member variables for the value of the node. And similar to what we did with our linked list, our doubly linked list, maybe I should say doubly, not double, but node pointers for the left and right subtrees. Right, but now instead of the node pointers being the previous and next, they're left child and right child. Okay, so provide a constructor and a default constructor. These can be, you can actually use the same constructor for both, I think. And then test this function with, so I want you to write sort of a sequence, for each question, or almost each one, you're going to write a little function testing that new functionality. So yeah, then using only the node class here. But then in question 4, we're going to make things a little bit clearer by introducing the binary search tree class. So make a BST tree. I think alternately I called it tree or just BST. I think maybe I had lost consistency there. Yeah, I see. Here I'm calling it just BST. And I forgot to go back and delete that. I suppose I could, as I find these errors, fix them. Yeah, like that D, I can delete that. And this, see what happens if I upload a file that I'm currently working on. Let's do that little experiment. Because what else have we got to do? Oh yeah, chapter 18. Okay. So I think it's question 4 where that was. Yeah, right here, huh? And do it like that, huh? Okay. So if I rebuild that, and then I go to here, oh, not there, here, and say files and upload. I'm going to grab that thing, countingtrees.pdf, replace. Okay. So then I go to assignments. Is it still looking at that same link? I want to open it with Firefox. Did I skip over it? I did. Okay. Alright, so okay, the D is gone, and now we're just calling this a BST. So we're going to make a BST class in how did that become int? Now I found another typo. BST.h header that stores a pointer to the root node, which might be null pointer, right? So in fact, if it's an empty BST tree, which we're going to allow for such a thing, right? In fact, the default constructor is just going to make an empty tree. It's like a tree with no leaves. Not even a root. we refer to the node at the top of the tree, which is as the root. So it's actually kind of upside down. So it grows down from the root. Or I suppose it's just conceptual, right? So you could easily draw it going the other way. It's very common to draw it going down, though. So it looks more like a tree, but the root is at the top. Yeah, I suppose it would look like a tree if you went the other way too. This way it looks like a conifer, like a Christmas tree. Anyway, yeah. And speaking of Christmas trees, should we take a moment to go off on a tangent? I am feeling the need to be tangential. All right. So, oh yeah, there's that. So what about Donald Knuth and the Christmas tree? Have we talked about this guy in his Christmas tree lecture? Yeah, so here's a link. There's a YouTube channel. Dancing Links, that was a good one. Here's one from last year. So I haven't seen this one yet. Explores pi in the art of computer programming. Wow. Okay, so his wife makes him these funny shirts, which sort of his signature in a way. And Donald Knuth is one of those guys who kind of created computer science, and he is the author of I don't know, shall I hold on a second? Okay. Here's can we see this here? It's backwards. Is that right? Why is it backwards? That's wrong. I think it's because if I'm facing this way, I want to be looking the other way. I don't know. But here, I think I can do. Does this work? I've got when I meet with my people. Yeah. Okay. So, The Art of Computer Programming by Donald Knuth. And this is volume 1, Fundamental Algorithms. And newly updated and revised. Oh, isn't that nice? So, yeah, I've got my page marked to, I don't know, what was I looking at? Oh, it's at the very beginning. So, but yeah. So this was a series of books affectionately dedicated to the Type 650 computer once installed at Case Institute of Technology in remembrance of many pleasant evenings. And this is the 3rd edition of this volume 1, and it I'm looking for the date. I don't know why I care. 1997. Okay, and you can see it. It's fairly thick. Okay, jam-packed full of algorithms. Here's a page. What are we looking at here? Am I looking at the wrong side? Yeah. So this is. Can you read that? Here. Multi-linked structures, right? I mean, just a random page 424, and you can see that if you really want to be a computer scientist, you will read all 3 of these. Here, let me show you another one. Do I have it here? Well, that's not worth finding, I guess. Yeah. That's enough show and tell, I guess. The concrete math is what I'm looking for. So let's go back to the browser. But yeah, so as easy as pie. And here's the video, right? So I don't think it'll stream, but you can see it's an hour long. That's typical, and it's his 25th annual Christmas lecture. I can hear it in my phones, but I don't think that goes across. In any case, yeah, I'll copy the link here and post it in the discussion. How about that? All right. So this is discussion, and here, yeah, something to do over the long summer months. Okay, so back to the assignments, and in particular counting binary search trees, which we're going to open not with Microsoft Edge, but with Firefox. Okay, and so we were at 4, so then provide a constructor and a default constructor and a print function declaration. I suppose I should have asked you to because you're going to be using the keyword new to allocate memory. So I should have asked you to write a destructor as well. Because you are responsible for this memory once you've allocated it on the heap. Heap allocated memory is your responsibility. And so that's actually, one of the hallmarks of, do you need to write your own destructor? And if your object creates memory on the heap, then yes, you need to create your own destructor. Okay, so then implement the print function, and so this tree here, for instance, should print like this, right? So what does that mean? Well, the root node is 5, right? And so I've got a node whose value is 5. Here's its right subtree, and here's its left subtree, right? And then this closing curly brace says that's the end of my tree because it's the end of the root node with its subtrees, right? So the left subtree is this one, which indicates that, yeah, it's got the value 4, and it's got an empty node as the left subtree and an empty node as the right subtree. Here's the right subtree. It's got same kind of thing, right? And this should be recursive, okay? So what I've actually done is given you a pretty big hint here, which is have print out this as the base case for the empty tree. So if your null point, if your left or right subtree pointer points to null pointer, then you just print out one of these pairs of empty curly braces. Otherwise, call this recursive function here. So you're going to have a function called, it's going to have the same name. I don't know, did I not indicate what the name is up here? All right, so you can have a function called subtree to string, and it's going to say if I'm an empty tree, just print out the pair of empty parentheses, and otherwise, actually I think this handles that, doesn't it? So you're right. So you're gonna have a string which is the left string, and if it's equal to if the left string is sorry, this is a ternary operator here. So here's the entire ternary thing, and is this true? Right, so this is a Boolean comparison operator. If the left subtree is the null pointer, then just print out empty curly braces. Otherwise, call this function recursively on the left subtree. So that's one string, right? So that's your left string. Then you're going to have your right string, which is going to do the same thing for the right subtree, right? And then, yeah, so this will do the whole thing, right? So so your output then is going to be, and are we missing some stuff here? It didn't fit on the page. What should that be? Okay, I think it's just, yeah, so plus right plus, yeah, so that's just the terminating. Can I do it like this? Am I live here? Yeah. So it's going to be, so this is a little plus sign here. So it's going to be plus the terminating curly brace. Can I make a curly brace? Which I suppose could be a string, not a character, right? So yeah. So it's just, so you're going to have your recursive calls here, right? So so the output is going to be you're going to call toString on the value there, right? So the value is going to be a number, and you're going to concatenate that with a comma plus the left string, and so yeah, maybe we'll have to play with that at some point. So yeah, put this. You'll be amazed at how this works. It's a nice example of double recursion, right? Because the first thing it's going to do, right, is, I mean, the subtree to string, first thing it's going to do is call subtree to string on the left node, and that left node may have a value, in which case it'll call subtree to string on its left node, and so on all the way down the left side until it finds the null pointer, at which point this is true, and we don't do the recursive call, right? Which means then we're going to call right, and it's going to, crawl back up and do the same thing for the right trees. And each right tree may also have a left tree, right? So it's going to call subtree to string on the right node, which is the first thing that's going to do is call subtree to string on the left node, right? So for each node, you've got a left node and a right node, and this is a marvelous way of just getting it all together in one nice string like this. All right. All right. So try testing this by inserting a pause. Yeah, so this is my suggestion here. Insert a little pause here after the first right string call, so you can see, well, here's what I got so far. And yeah. All right, so then we don't have any way of actually building these trees yet, right? So to build other than sort of stitching them together by hand, but that's awkward, right? I think actually in number 2, I ask you to do that with just the node thing. So you can actually build a tree by stitching it together manually. But the more elegant way of doing that is to have the binary search tree include a function called insert, which will take the value of the node you want to insert there and call it. So this is the one that has the helper function to get started, right? Yeah. So I'm sorry, I'm missing a parenthesis here, huh? Can I fix that now? Was there something else I needed to? Oh, I wanted to like not have this scroll off to the right. So I wonder if I can. Let me. Yeah, we do this in real time, people. So we're going to go in here and make this so that it all fits. Which, to be consistent, this means it's going to be significantly shorter. And then down here, I'm missing a. So which question was that? Question 6. Okay. Yeah. Okay. Was there anything else? Yeah, probably, right? I think that's good. So I'm going to go F1 on that. And then I'm going to go back here to files and upload this counting subtrees PDF file, okay, and replace. Okay, then go back to assignments. I mean, it's just a lot easier to read something that doesn't have typos in it. For God's sake, stop it with the typos. And okay, open with other. Okay, so I probably have a bunch of these things open now, right? Yeah, this was the previous one. This is the one before that. Okay, so so now we're down to number 6, and right. So you're going to have this insert function. You're actually going to have 2 functions with the same name, insert, which means we're overloading, and the second one will have 2 parameters. This is where we were missing our parenthesis. Oh, can you not read that down there? This is where we were missing our parenthesis, right? So, so this second insert function will be called by the first insert function. I guess that's a recursive call. I mean, certainly the second insert function will be recursive in sort of the same way that the subtree to string function was recursive, like doubly recursive, right? So you recurse to the left and you recurse to the right. And the beards will all grow longer overnight. All right. So this is kind of a helper function. The reason we need a little helper function here is because the first node is going to say, well, if you're trying to insert into an empty tree, right? So if you're inserting into an empty tree, then you should just create. Notice the use of new here. So we're actually allocating memory on the heap. Now I tried to do this with an ampersand here instead of new, so I just say make root the address of a node, right? Well, what is root? Root is a pointer to node, right? So we go up here. what is in 3 or 4, where we introduce the binary search tree, and we see that it could be the null pointer. A root node could be the null pointer. So here's your helper function. And if there is something in the root node, then we're going to call insert on with that value that we want to insert, and whatever is in the root, and it's going to say, well, point to the, call insert to the left and call insert to the right until there's nothing left to insert. And then, yeah, write another function to test that. Okay, so if you follow to here, then your insert function may be generating copies of a node pointer each time it's called. Right, because you're using new, well, yeah, it's not just that you're using new, but you're generating local copies. So the way to avoid that, as usual, is to pass by reference. That's a particularly interesting object there, right? So it's a reference to a pointer to a node. Now, generally speaking, when you see these two things next to each other, they kind of cancel each other out, right? If this is the dereferencing operation, which if this were to the left of a pointer, it would dereference it, right? And so if you dereference an address, then you're getting the thing at that address, right? So you might as well just have the thing. But putting them to the right here like this has the added benefit of then not making local copies in your function of all those things, and accessing them by reference instead of by value, which will make copies, right? And then number 8, write a function that will input a binary search tree. So it takes as an input a binary search tree, and then return a tuple, right? So you may not have dealt with these tuples before. The nice thing about a tuple is that they can all be different types, and it's a single object, right? So it's one object, which is a tuple. So it used to be that it was a real constraint of C++ and C that you couldn't return more than one number. Of course, you can always return an array or a vector of objects, which is one thing, and so it's very much similar to that. But a tuple, the nice thing is with an array or a vector, they all have to be the same, and here they are in fact all the same. But why not use this tuple thing, just so you're aware that it exists, and you can actually make these three things different types. All right, so you got a character, an int, and a double. In this case, they're all going to be ints because they're going to tell you how far does your tree extend to the left, how far does it extend to the right, and how deep is it, right? So in this case, it goes 1, 2, 3 to the left, so that first number is a 3. It goes 2 to the right, the second number is a 2, and it goes 1, 2, 3, 4 down, so the third number is a 4. And that's sort of in preparation for number 9, which is write a little SFML routine that given a BST, will draw it to a graphics window showing circular nodes. So this is so you know how to scale the tree in your window, right? So you would put the root towards the middle top, right? And then you'd have potentially, the half to the midpoint of the half to the left and the midpoint of the half to the right, and you would put the 2 and the 8 at those positions, and continue doing that, I guess, recursively until you've written all the nodes. And then how far down should each node? I guess that would depend upon the depth, right? So you're gonna have to do a little pencil and paper geometry is typically how I do that with, sort of I've got this much space I need to like mark off, and it's very much sort of practical planning as to how you're going to make things appear in the window with lines and circles and text, actually, right? Because you're going to have to put the value as a text object in the position where it belongs. I suppose you could, I was saying you could use your pool balls as texture objects. But no, we don't. Yeah, I mean, what if you have more than 15, right? So, yeah. So just trying to, what if you have hundreds of them? Then you got a 3-digit number you got to fit in your circle. Let's say that, you're not going to have, you're going to have less than 100 nodes. It turns out the number of trees you can make sometimes gets very large. Now notice if you have a tree, maybe I should mention this as we're doing this. If you have a tree with like 1, 2, these are separate numbers, right? 3, 4, and so on like that. How many trees are there how many sequences are there that will make this tree? Well, only one, right? Because it's got to go 1, 2, 3, 4. So there's no choices, right? The root has got to be the root, and the next has got to be the next, and so on. So there's only one in that case, right? But if you were to go like 1, 2, 4, 3, I think now you've got 1, 2, 4, 3. Is there only one of those again? Yeah, like there's no actual branching anywhere. So yeah, this is another oneer, right? So how about 1, 3, 2, 4? And you have the 1, the 3, and then now you got a branch, right? So the 2 and the 4 could be reversed, and this is I think I've said this before, but it bears repeating. Almost everything a computer does, well, no, take that back. If you look at what do computers around the world spend most of their time doing, searching and sorting, right? And a main structure for doing that is the binary search tree. It's much faster to search through a binary search tree than it is to search through random data, right? So oftentimes what you do is, as you get your random data, you build a binary search tree from it, so that the next time you need something from that data, you can find it in a hurry. All right, how are we doing? So I think, okay, so I guess what else do we have to say about assignments? Let's see. Well, there are other assignments, and billiards. I'm getting to it. It's on my it's in my in pile. I'm still like giving myself more in pile objects potentially, but this is the last assignment, I think. So I don't know. I might put together that one I was talking about with the Huffman codes and Morse codes and steganography, but this is the last one where I have a 2-week interval for you to do it in. All right, for sure. So any questions about that? Should we look at these other ones? The key to cryptography. Should we see? I don't know what's happening in there. I need to read this still. I'm sort of hesitant to read it in public. So there's something called speed grader. This student does not have. Okay, so oh, Mark, no, did you know that you didn't have the? Maybe I should extend the deadline for this, because looks like a lot of people haven't done this. No preview available. Okay, so maybe this is a big fail, right? So I think, did I grade some of these and not all of them? Is that what happened? Yeah, so this one was graded, right? So some of these I did grade, but can I fix the fact that it's overdue. Is it overdue? I don't know. Let's see. Can I go back? No. Okay, did I just close that window? Okay, yeah. So, edit assignment settings. Is this a thing I can do here? Yeah. Oh, yeah. See, this is an external thing. I think I have to do it in there. So if I go to My Open Math, which is here. Oh, this is 7B. Sorry. And oh, I think this was actually in a 7A shell. So maybe let's look at that. Or maybe it wasn't. Where the hell was that? So here's 7B. Oh, maybe I need to open up one of these. Yeah, here it is, key to cryptography, right? And so if I go to settings, I can see show by dates, available until 5/13, it says here. Oh, actually it says always after start date until the course end date, which is June 12th. No, it's not. It's May 22nd. Well, I think yeah. Should we give it a more hard date here? We can say, oh, how about May? This is, oh, we said we'd go a week after. Okay, so how about that? All right, so it's still available. If you haven't done it yet, you might want to give that a little shot. It's just a 10-pointer quiz, so it's no big deal. All right, and I guess we're done with that, aren't we? Okay, can we go back to here and say assignments? And so then there's the end body part 2, the billiards I haven't finished reading. Well, I started reading it, and I blame Anthony for giving me something really hard to read. Okay. What do we have? Did you grade the response portions of the key to cryptography? The free response. That's what you're telling me. Right. No. And right. So, yeah, where do I think I do that in, well, let's see. Can I do it here? So if I open that up, okay, this is not, yeah. I want to look at your responses, right? So this would be the way I would take the darn thing. And if I go here, what is it? Questions, settings, grades. Okay. Yeah, I'll figure this out on my own time. It's been a while since I've fussed with this, and so, yes, thank you for keeping me honest. I didn't see that the assignment had extra stuff in it. Yes, it did. Sorry. I know things are not always as obvious as they should be. I know you're all very good about trying to figure out what the hell there is, despite my obfuscations. All right, so I'm going to go back to here, and then I'm going to go back to the discussions and see what the hell. Oh yeah, chapter 18. Okay, well, let's go there, and for that we'll need to open up, I don't know, where are we in chapter 18? Essential operations. I think we were like, yeah, okay, so if we go to, where are we here? Over here, can I go to, yeah. Okay. And we had talked about some code last time, which was the chapter 17 stuff. So let me get my code window working here. And that looks like not this. So let's close that out, and yeah, okay, so not this either, but that is the one that I want to have access to. Okay, right, so let me exclude this from the project, save it, and add existing item. So you know what I did was what was that copy idiom? What's it called? Copy and swap idiom. So let's open that up and take a quick look at it, since we talked about this last time. And this is the link here. Should I go ahead and post that up into today's discussion? So if I go back to the browser and open up this discussion here, I can post another reply. Oh, I should reply to this, right? Which is uploading that code. So this is where 7B, okay, and copy swap idiom. Doesn't seem to be there, right? Because this is there. I think I want this. Okay. The copy swap idiom, and yeah, so if you want that code, it's posted here, and we can go back and look at it. I think in the code I put the Stack Overflow link, right, so you can get there if you like. And this is creating the dumb array class, which is kind of like what our simple vector, our user defined vector, not the standard template library vector. What we're doing in chapters 17 and 18 is build this vector class, and it's got so this is a default constructor because there's a default value for the parameter. So if you don't give it one, it'll be 0. So you can just say dumb array with empty parentheses, and it'll understand that you're passing in size 0, which will then be assigned to this member variable msize. And then the array, this is a little bit different way of building the array. We're using the ternary operator, so it says is msize not 0? If so, then allocate memory for msize integers on the heap, and if it is 0, then just make it the null pointer. Okay. And what I had something here for initializing these. Yeah, I wanted to mention that. See those parentheses there, right here? Why are they there? Well, because that's calling a default constructor for an array of ints. And so if you put these parentheses here, you get an empty, not an empty array. What am I trying to say? You get an array of msize integers, all 0. So because that's the default value for an int, right? So while I had this code down here, it's not needed because of the parentheses above, right? All right. Now I wrote a couple of a getter and a setter here functions so that we could actually test this thing, which do the obvious stuff. Then there's another constructor here. So this is a copy constructor. Maybe I should make a comment here, right? And it's got an initialization list. which is going to say, yeah, take other dot size, other dot m size or whatever, and make that the size of our array, and then again this is part of the initialization list, right? So you're going to initialize our local array by if there's nothing in the array we're copying, then just make it the null pointer. That's easy enough. Otherwise, allocate. Should we? Yeah. See, now we're not going to make. We're going to need to copy these elements. So here we're just allocating the memory on the heap for these elements, and then down here we're using this copy function that we had so much trouble with last time, but seems to be working here, right? Which is taking an iterator. Well, is that an iterator? I guess it's not. It's just a raw memory address, right? I think copy will take iterators, but it will also take just raw memory addresses. So an iterator is more than just a raw memory address. It's got like a little wrapper around it. All right. I guess well, I'll say no more. And then, so this is the starting address, right? The name of the array is the address of the first element of that array, right? So this is the array being passed in where here, other. And so this is the memory address of the array we're copying. And then this is one past the last element of that same array, right? This is what's called pointer arithmetic, right? Yeah, well, you add, right? So we're adding. So M array is essentially the address of an integer, right? In that sense, it's very much like a pointer, right? Yeah. And so when we add to a pointer, a number to a pointer, says, well, what kind of object does that pointer point to? Well, it points to an int, right? So when we add m size to that pointer, it's going to add what each integer takes 4 bytes, right? So it's going to add 4 times m size bytes to whatever address is here. And that's your stuff that you're trying to copy. It's all right there, right? And where are we copying it to? Well, our local member variable marray, right? Marray is not others marray. It's the calling functions, right? It's yeah. We're constructing a new dumb array, and it's going to be located here. All right. So then, so here's the move semantics, right? So when you see that ref in this way, that means we're doing move semantics, and we'll maybe have to talk about that. And now, since we've allocated memory on the heap, we're responsible for deleting it. I'm feeling guilty about your project where I didn't ask you to do that. You should do that. Just because you're not asked to, you're still responsible. It's implicit in the heap. Heap allocated memory is your responsibility. I feel like a parent or something. All right, so how are we doing? Okay. All right. So then, yeah, this is our usual stuff down here, right? So then here are his comments about this. I don't know, whoever wrote this Stack Overflow article. So here's the hard part. So he does this naive version of overloading the assignment operator. And what makes it naive? Well, there's a few things, right? 1, 2, and 3, which he addresses down here. So he says the first comment he wants to make is about the self-assignment test. So if so this is a pointer to the object in whose context we are, and if that's different than the address of the thing we're essentially this is like a copy constructor, only using the assignment operator. So we're trying to copy the thing on the right to the thing on the left, right? If the thing on the right is the same as the thing on the left, then we don't want to do all this, right? We're going to skip it. So that's the self-assignment test. Now what does he say? This check serves two purposes. It's an easy way to prevent us from running needless code on self-assignment, and it protects us from subtle bugs such as deleting the array only to try to copy it. But in all other, which is what we were doing before, right? Yeah, we found that if we put in that self-assignment test, then we wouldn't have that problem of the thing being deleted. But in all other cases, it merely serves to slow the program down and act as noise in the code. Self-assignment rarely occurs, so most of this time this check is a waste. It would be better if the operator could work properly without it. So what's happening here? Why are we assigning the null pointer to mArray? Well, before we do that, we delete mArray. Right, so we free up the memory associated with the thing that is calling the assignment operator, which is the dumb array on the left, right? So you imagine, dumb array on the left equals dumb array on the right. We're trying to copy the array on the right to the one on the left. Does the one on the left exist? Presumably, yeah, right? And so in order to copy something else to it, we need to free up its memory. So there it is, right? So what does he say about that? The second is that it only provides a basic exception guarantee. Right? The idea is that if the allocation for new memory fails, then dereferencing this, well, the actual object that we're assigning to will have been modified. Namely, the size is wrong and its data is gone. For a strong exception guarantee, it would need to be something akin to, and he's showing this code here. So, what were we doing up here? We were deleting the old memory and then assigning the null pointer to that memory. So down here instead, we're saying copy to our new size. Declare a variable of type size _t called new size to have the value of the right operand's size. So we've made a backup of that, and then use the ternary operator here to say, is new size bigger than 0? If so, then allocate memory on the heap for that many, and notice that this is initialized to 0. Yeah. And assign the memory address of the first of those objects to new array, which is a pointer to an int. Then call the copy of others data to this new array. then replace the old data. So now we delete the old data. We've got something called new array, which we assign to our data, right? And we sort of prepared for this to happen, and now we have a better guarantee of not throwing an exception. And then we return this object. So then in the part 3 up here, was it up here? Yeah. What's happening here? Yeah. Oh dear. People feel free to just walk their dogs around here. We don't have that problem on campus. Not a lot of dog walkers out the window. More importantly, my dog is not in the classroom, looking out the window, seeing other people walking their dogs. Just saying. So wait, what's happening here? So M size and put the new. Okay. So we copy M size and copy the data. So he's saying the problem with that is that the code has expanded, which leads us to a third problem, code duplication. Our assignment operator effectively duplicates all the code we've already written elsewhere, and that's a terrible thing. In our case, the core of it is only 2 lines, the allocation and the copy, but with more complicated, complex resources, this code bloat can be quite a hassle. We should strive never to repeat ourselves. All right. Say something once, why say it again? One might... All right, hold on a second. Okay, we're about 15 minutes away from the break. One might wonder if such code is needed to manage one resource correctly. What if my class manages more than one? While this may seem like a valid concern, and indeed it requires non-trivial try-catch clauses, this is a non-issue. That's because a class should manage only one resource. Yeah. So if you find yourself writing a class that manages more than one resource, yeah. What about our tree class, our binary search tree? No, it's just a network of node pointers, right? That's essentially one resource, right? Those node pointers are the resource, and that's the only kind of resource we have. Interesting. Okay. As mentioned, the copy and swap idiom will fix all these issues. But right now, we have all the requirements except one, a swap function. While the rule of 3 successfully entails the existence of our copy constructor, do we remember the rule of 3? If we allocate heap memory, then we probably have to write all 3 of those default things, right? The destructor, the copy constructor, and the overloaded assignment operator. I think those were the big 3, right? Yeah. Oh, sorry. Yeah. Copy constructor, assignment operator. There they are. They're written right there, right? Yeah. It should really be called the big 3.5. Anytime your class manages a resource, it also makes sense to provide a swap function, which is only half a thing. So we need to add swap functionality to our class, and we do that as follows. So here's a little swap function, and it takes 2 dumb arrays by reference, first and second, and it's using the standard template, the standard library swap function. I guess that's to avoid variable collision there, right? You may have another swap function somewhere. We want to say no, swap refers to the standard swap. So we're going to swap both the size and the arrays. By swapping members of two objects, the two objects are effectively swapped. And this is done without, yeah. So I think what's kind of lurking in the background here is there's a fancy, so if you've written your own swap thing, right? You have to create a temporary variable, and then as a backup of the first object, and write the second object to the first object, because you backed it up, you still have it available to write to your first object, right? Turns out there's a way of doing that without that temporary variable. Should we maybe, I don't know, I hesitate to go off on a tangent. What? That would be a first. So let's go to the browser, and where can I do this? Oh, by the way, see, tangents inside tangents. Let me post this up to the discussion as well. This is a really nice collection of the math community, computer science community. Where they overlap are a bunch of people right now, and they all are remembering the work of John Conway and Richard Guy. And so this is freely available. This is stuff that's often behind a pay screen, but they've made it freely available. So where shall I put this? I don't know. Here? I guess I was going to put something there. There. Okay. I had opened up a reply and never put anything in it. Okay, so a bunch of tangents to go off on, folks. Okay, let's return from that tangent and go back to our other tangent. I think I can use this space all right. So C++ swap without temp. Let's see if there's any. How to swap two numbers without using a temporary variable. Geeks for Geeks. Geeks for Geeks usually doesn't let me down. Sometimes they do. Method 1, using arithmetic operators. Oh, I don't know if I've seen this one. Without using a temporary variable. So suppose you want to, so x is 10 and y is 5, and you want to swap x and y. Well, you say x, so you're not creating a new variable, right? You're still just in the confines of x and y. So you add y to x and make that the new x. All right, and then you subtract y away from x, and that's the y. That's the new y. And then you take y and subtract it from x. X becomes 5. Does that work? Wow. God damn, that's clever. Wow. There's another way? You could get, it was a multiplication and division can also be done. Is there a third way? Using bit. This is the one I was thinking about, but apparently there are these other ways of doing it, right? But it was this bitwise. So the bitwise exclusive OR operator can be used to swap two variables. So the exclusive OR of two numbers x and y returns a number which has all the bits as 1 wherever the bits of x and y differ. For example, the XOR of 1, 0, 10 in binary is 8 plus 2, right? So that's 1, 0, 1, 0. and 5 is 4 plus 1. So the XOR of 10 and 5 is 1, 1, 1, 1, right? Because you XOR 1, 0, 1, 0 with 0, 1, 0, 1, and you get 1, 1, 1, 1. Does that make sense, right? And the XOR of 7 and 5, yeah, so they give a couple of examples, right? So the XOR of 7 and 5, well, they have the 1 and the 4 in common, right? So the XOR of 1 and 1 is 0. But 7 has a 1 in the 2's place, and 5 has a 0 in the 2's place. So they get a 1 in the 2's place when you XOR, right? So how does that work in the code then? So if you say, yeah, x equals XOR, x XORed with y, right? So 10 and 5, if x were 10 and 5, that would then be 15. And then you take y and XOR it with 10, you're going to get 1, 0, 1, 0, right? Which is 10. That's what y used to be 5, and now it's 10. And then you XOR x with y, which is now 1, 0, 1, 0, and x is 1, 1, 1, 1, right? And you get 0. Wow, that's really slick, huh? So there are all sorts of fancy ways of swapping things without allocating new resources. I think that's the basic line. Maybe I'll post this in the discussion as well, right? Because that seems like an important idea that for what we're doing here with this swap routine. Don't forget to post. All right, and all right. So I went off on a tangent, and now I'm going back to where we were. So we're able to swap these things without allocating new memory. Okay. I think, is this the same link as before up here? Oh no, this is 3. Okay, I'm not sure. So which one is this? Oh, okay, so this is the explanation of why public friend swap. Okay. I don't know, maybe should we go to there as well? I would like to get to the exercises for chapter 13. Does anybody know about the... Here's another tangent for you. The Office of Post-Secondary Education has an emergency relief fund. This is for students. And I'm not sure if this information has gotten out or how, but later on today I'm going to be pursuing what's going on with our administration and this fund. Right, we want to make sure this fund doesn't go to the administrators. They're pretty good. Well, I'll take half of that, and you take the other half. There. Now we've allocated it. Okay. So in any case, there's another tangent. Okay, so I'm gonna. We've already. Okay, we don't need this anymore, right? That was from last Monday. Okay, so public friend swap member. In the beautiful answer to the copy and swap idiom, there is a piece of code I need a bit of help. All right, so this is referring back to that, okay? He says here, so there's sort of a back and forth between these two Stack Overflows, huh? There are other claims that we should specialize swap for our type, provide an in-class swap alongside a free function swap, etc. But this is all unnecessary. Any proper use of swap will be through an unqualified call, and our function will be found through an, what's an ADL? One function should do. I should know what an ADL is. An ADT is an abstract data type, right? arithmetic. And our function will be through I don't know. Gosh, now I'm off on another tangent. So data type ADL, is that what that is? Oh, it's a language? Azure Data Lake? ADL heat map? See, it's like acronyms. There's, not enough acronyms for all the things we want them. Okay, algebraic data language? No way. Really? There's a GitHub site devoted to it. Anybody know what an ADL is? I suppose I should know. It's like, I should still have that note I had on my door in graduate school, which said, "The number of things I know nothing about is getting larger every day." I don't know, what is this? Is there abstract data language, a framework for building cross-language data models? It consists of a DSL for describing data types, and okay, well, let's say maybe there's an algebraic data language. Yeah, that's what it is. So where were we? Yeah, here. All right, well, we're right up on the break here, so maybe I'll just leave this here for your consideration while we take. Let me ask if there are any questions about anything. Yeah, thanks for reminding me about the free response portions, because what's sad about that is that you don't get credit for them. It looks like you got a terrible score, when in fact all I need to go through is read those and give you credit for them. I perfectly understand having some angst about that. All right, well, seeing nothing, I will pause the recording and see you in 10 or so. All right. That's just enough time for me to stroll over to the little math building and replenish my coffee, which is actually tea. So where were we? Right, we were talking about this swap routine. Do you know, please, if the standard template library contains a binary search tree implementation? Oh, well, no, that's a different one. Sorry. Let me get rid of that. Was it here? Not sure. It was a Stack Overflow thing, and I got a bunch of them running around here. Yeah, no, it's not that one. Oh, okay. Yeah. With friend, I am still a bit on unfriendly terms, I must admit. So here are the questions. It looks like a free function, but it's inside the class body. Yeah, so friend functions are a little weird, right? It means you're a function that has X. So other functions will have access to the... Yeah. So why isn't this swap static? Static, right? So that's another way of... It obviously doesn't use any member variables. Any proper use of swap will find out swap via algebraic data language. We'll search. I don't know what ADL stands for. But does it also look inside classes, or is that where friend comes in? And so do we have responses here? There are several ways to write swap, some better than others. Over time, though, it was found a single definition works best. Let's consider how we might think about writing a swap function. And but we're just sort of using the standard template library swap, and it's written the correct way. Oh, look, here's a link to ADL. Argument dependent lookup. Argument dependent lookup. Yeah. Okay. All right. Well, let's leave that sidebar and get back to our code. Otherwise, we'll never get anywhere, right? Any questions about that? Yeah, I mean, I'm sure I have questions about it, so you do too. But let's, if there's anything you can articulate right now. Um, so, right. So this is that's that link there will take you an explanation why it's a public friend swap. I haven't finished reading that, but I plan to. So now not only can we swap our dumb arrays, but swap in general can be more efficient. It merely swaps pointers and sizes. I got to say, Strustrup is not using swap in chapter 18. So when we get back to that, we'll have to sort of take note. Well, how's he doing it? Rather than allocating and copying entire arrays, right? Aside from this bonus in functionality and efficiency, we are now ready to implement the copy and swap idiom. So here it is. Damn. Right? All that other crap, gone. Remember, we had lines and lines of code. Well, we need to like make a backup of this and a backup of that, and then make sure this is not. No. You just say, okay, look, I want to assign the thing on the right to the thing on the left. Here's the thing on the left, right? That's a dereferenced dumb array pointer. And here's the thing on the right. You just swap them without allocating new memory, and you return what is now the thing on the left, which used to be the thing on the right. And that's it. With one fell swoop, all three problems are elegantly tackled at once. Why does it work? We first notice an important choice. The parameter argument is taken by value. Oh, yeah, that's a big difference here. Did you notice that? Right, so up here, the assignment operator, where is it? We're overloading the assignment operator somewhere. Oh, was it down further? Yeah, that's the swap function. No, it was up, oh. Yeah, I guess it was sorry, it was in these things that are commented out, right? So here we're passing by reference, right? Sorry, yeah, passing by reference, meaning that we deal with the actual object, not a copy of it, right? But down here, when we're overloading the assignment operator finally with this swap thing, we make a local copy of the other. Right, because it's passed by value. Is that what that means? Well, it's not the whole thing, right? Other is the name of the dumb array, which is got bundled in with its size and a pointer to the first element. So we're making a copy of the name, not the whole thing. Okay, so the parameter argument is taken by value. While one could just as easily do the following, and indeed many naive implementations of the idiom do, all right, you pass by reference, and you know, you're returning a reference. We lose an important optimization opportunity. Not only that, but this choice is critical in C++11, which is discussed later. On a general note, a remarkably useful guideline is as follows. If you're going to make a copy of something in a function, let the compiler do it in the parameter list. So the compiler's handling it. Either way, this method of obtaining our resource is the key to eliminating code duplication. That's like counterintuitive, right? Because we're eliminating code duplication by making a copy. Well, no, we're eliminating. We don't have to like write all those operations over again in the code. We get to use the code from the copy constructor to make the copy, and never need to repeat any bit of it. Now that the copy is made, we're ready to swap. Observe that upon entering the function that all the new data is already allocated, copied, and ready to be used. This is what gives us a strong exception guaranteed for free. We won't even enter the function if construction of the copy fails. Okay, and it's therefore not possible to alter the state of the calling object. What we did manually before for a strong exception guarantee, the compiler is now doing for us. How kind. At this point we are home free because swap is non-throwing. Okay, so there's no catch exception. So we swap our current data with the copied data, safely altering our state, and the old data gets put into the temporary. The old data is then released when the function returns, whereupon the parameter scope ends and its destructor is called. All right, so that's sort of key to this move semantics, which is, I guess, what we're going to get up to next, right? So because the idiom repeats no code, we cannot introduce bugs within the operator. Okay, and all right. Note that this means we are rid of the need for a self-assignment check, allowing a single uniform implementation of the assignment operator overload. Additionally, we no longer have a performance penalty on non-self assignments. That is the copy and swap idiom. What about C++11? Well, the next version of C++, and this was when C++10, I think, came out that this article was produced, makes one very important change to how we manage resources. The rule of 3 is now the rule of 4.5. Why? Because not only do we need to be able to copy construct our resource, we need to move construct it as well. Luckily for us, this is easy. So here is the definition of the move constructor, and it's got this no except, right, qualifier that means it's exception, because the exception is guaranteed, right? And here he's using the swap function again, right? So we're doing a copy constructor through the move, but it's actually just the same code as the assignment operator, right? Except I think we don't need the return, right? Yeah. So what's going on here? Recall the goal of move construction: to take the resources from another instance of the class, leaving it in a state guaranteed to be assignable and destructible. So what we've done is simple. Initialize via the default constructor, a C++11 feature, right? Then swap with other. We know a default constructed instance of our class can safely be assigned and destructed, so we know other will be able to do the same after swapping. Note that some compilers do not support constructor delegation. In this case, we have to manually default construct the class. This is an unfortunate but luckily trivial task. So we didn't talk about writing our own default. It wasn't part of the rule of 4.5 that we had to manually write our own default constructor. But why does that work? That is the only change we need to make to our class. So why does it work? Remember the ever important decision we made to make the parameter a value and not a reference. Right here, right? Now, if other is being initialized with an R value, that's the right side, right? It will be move constructed. Perfect. In the same way that C++3 let us reuse our copy constructor functionality by taking the argument by value, C++11 will automatically pick the move constructor when appropriate as well. Yeah. And of course, as mentioned previously, linked article, the copy moving of the value may simply be elided altogether. And so concludes the copy and swap idiom. And there's some footnotes here. And here I've implemented this. I have yet to implement the move constructor, right? But so what am I doing here? I'm creating a dumb array. I'm making another dumb array with 3 elements. I think those are then all the 0, right? We get the default that way. And I'm going to print out the elements of DA2, which should all be zeros. Then I'm using the copy constructor to copy DA2 to DA3. Then I'm going to change DA3. Its first element will be 17. Then I'm going to print both of them out and see what we get. And then we're going to have a 4th dumb array, which is using the assignment operator to copy the... And the assignment operator here is that just using the copy, is just piggybacking on the copy constructor with the swap routine, right? We're going to set the second element of DA4 to 42 and then print out what it is. Okay, so let's go ahead and see if that doesn't work. And here's the output window. You see, yeah, our DA2 was all zeros, 3 zeros. DA3 was, so we copied DA2 to DA3 and set DA3s to 17. Then DA2 stayed at 0, 0, 0. Right, so they're not pointing at the same memory. One is a copy of the other, but in a different memory location, so it's not just an alias. And then DA4, we can do a similar operation. Okay, we better get back to the book or we never will. So we're in section on initialization. I think we've been through this. So copying, right, is where we were. We talked about this. Copy constructor, we talked about that. So copy assignments. Right, we kind of talked about that, right? Copy terminology was kind of where we were leaving off. We were talking about shallow copy. Only copies a pointer so that the 2 pointers now refer to the same object. Right, that's kind of what we want to avoid. I mean, why? I mean, sometimes it's neat to have an alias, but if you want a separate object, which is a copy of this object, then deep copy is the way to go. And so, I'll give you an example of deep copy, shallow copy versus deep copy, right? And then we got on to moving. So that's 18.3.4. And maybe look at this. If a vector has a lot of elements, it can be expensive to copy, so we should copy vectors only when we need to. So consider an example here. So we've got an input stream reference IS, and we've got a function called fill, which returns a vector. We reserve, or what's, I'm not sure, vector res. So for every, so we're going to input into X a double, and then push that back onto our vector of doubles, right? Our abstract data type vector is, by default just doubles. It's not a template object, right? And then we're going to use it to create a new vector called vec and assign it the output of this fill function, which returns a vector. Here we will fill the local vector res from the input stream and return it to use. Copying res out of fill and into vec should be expensive, but why copy? We don't want a copy. We can never use the original res after return. In fact, res is destroyed as part of the return from fill. Right? When it goes out of scope, the destructor is automatically called, right? So how can we use the copy? Consider again how a vector is represented in memory. It's got a size element and then a pointer to the first of its elements. We would like to steal the representation of, remember this this idea you're stealing the representation of res to use for vec. In other words, we would like a vec to refer to the elements of res without any copy. After moving res's element pointer and element count to vec, res holds no elements. We have successfully moved the value from res out of fill to vec. Now res can be destroyed simply and efficiently without any undesirable side effects. Okay. Should we put this on the so exclude this from the project, and I'm not sure where we are because it doesn't necessarily match the section numbers the way they sometimes do. So I'm going to add existing item and 18.4.1 I'm going to say maybe. Let's open that up and see what it is. Well, yeah. Oh, there's 18.3. I think we went past it. Okay, so exclude that and get new excuse me, a existing item, which is going to be 18.3. There's only a few. There's a few 18.3s. Well, there's only two. Right. So the first one is this one, and oh, that's not what we want, right? Oh, you're not looking at it, are you? Code. Okay, so I'm going to go to here. So that's 18.3. I'm going to exclude that. Not sure what that's for. And so add existing item 18.3.1. Should we look at that? And this is kind of interesting, but it's not where we are. We haven't read this part yet. So let's maybe go. Maybe this is actually the old 18.2. So I'm going to exclude this again and go back to here and say add existing item 18.2, of which there were a few. How about 2.3? Yeah, it could be that they were rearranged. I keep getting lost in this section. So exclude, that was 18.3, 2.3 I think. Add existing item. What if I go to 18.5? Nope. Yeah, I'm just not finding this code. Well, that's all right. Let's just read it. I'm sorry. Okay, so we have successfully moved. How do we express such a move in C++ code? We define the move operations to complement the copy operations. And so here it is, right? That's the move constructor. And the funny ref notation is called an R-value reference. We use it for defining the move operations. Note that move operations do not take const arguments. That is, we write vector ref and not const vector ref. Part of the purpose of the move operation is to modify the source to make it empty. The definitions of move operations tend to be simple. They tend to be simpler and more efficient than their copy equivalents. So for vector, we get this. So here's a definition of this thing, and we have the initialization list, and we initialize, make the and then we make it empty, huh? And then here's the assignment operator taking a ref object. So you know the move constructor copies the data element, and the size from A, and then it makes the empty vector. So if we want to move this vector using a ref operation and the overloaded assignment operator, we deallocate the old space, copy A's element size. See, now this is looking kind of like what they were using swap to get rid of, which maybe that's a better way. And then make the empty vector and return a self-reference to this. By defining the move constructor, we make it easy and cheap to move around large amounts of information, such as a vector with many elements. So consider again this fill function. The move constructor is implicitly used to implement the return. The compiler knows, so implicitly, right? The compiler knows that the local value returned res is about to go out of scope, so it can move from it rather than copying. Warning: the importance of move constructors is that we do not have to deal with pointers or references to large amounts of information out of a function. Instead of this flawed but conventional alternative, right, so here's the flawed conventional alternative, which is to pass by reference, to allocate new memory, and enter from some input source into that new memory, and then return that. We just do this. Oh, well, no, this is using that, right? Now we have to remember to delete the vector. Right, so with this style, you have to remember to delete the vector. As described in chapter 17.4.6, deleting objects placed on the free store is not as easy to do consistently and correctly as it might seem. Right, we've seen that. So 18.4, which takes us into the middle of chapter 18. I know there's still a ways to go here. We still have to do access and arrays and the palindrome example. All right. So we have now reached the point where we can discuss how to decide which constructors a class should have, and whether it should have a destructor, and whether you need to provide copy and move operations. There are 7 essential operations to consider. Constructors from 1 or more arguments, the default constructor, copy constructor, the copy assignment, the move constructor, the move assignment, and the destructor. Usually we need 1 or more constructors to take the arguments needed to initialize an object. Okay, so for instance, suppose you want take the string cat.jpg. So we initialize a string, and then we want to initialize a point, a graphics object point, right? with those coordinates and then display the contents of this image file at that location. The meaning use of initializer is completely up to the constructor. Standard strings constructor uses a character string as the initial value, whereas images constructor uses the string as the name of the file to open. Usually we use a constructor to establish an invariant. If we can't define a good invariant for a class and that its constructors can establish, we probably have a poorly designed class or a plain data structure. So constructors that take arguments are as varied as the classes they serve. The remaining operations have more patterns. How do we know if a class needs a default constructor? You need a default constructor if you want to make objects from the class without specifying an initializer. Right. So the most common example is when we put objects into a class in the standard object in the standard library vector. The following works only because we have a default value for int, string, and vector, right? So, right, for doubles it's 0, for string it's the empty string, and for vector it's the empty vector. So having a default constructor is often useful. The question then becomes, when does it make sense to have a default constructor? The answer is when we can establish the invariant for the class with a meaningful and obvious default value. For value types such as int and double, obviously 0. For the string, the empty string. For the vector, the empty vector. A class needs a destructor if it acquires resources. A resource is something you get from somewhere and that you must give back once you're finished with it. So the obvious example is memory that you get from the free store and you have to give back. Our vector acquires memory to hold its elements, so it has to give that memory back. Therefore, it needs a destructor. Other resources that you might consider as your program increases in ambition and sophistication are files. If you open one, you have to close it. Locks, thread handles, and sockets. Another sign that your class needs a destructor is simply that it has members that are pointers to references. If a class has a pointer to a reference member, it often needs a destructor and a copy operation. So a class that needs a destructor must also almost always also needs a copy constructor and a copy. So right, so this is like the rule of 3, right? We were talking about. All right. So explicit constructors. Consider the complex class here. Implicit constructors should be used sparingly and with caution. So what is an implicit constructor? Well, let's see. Okay, so here's our constructor that takes a couple of doubles. And, oh, I see. When we define Z1 to be a complex number and we assign it to 3.14, which is just a double, the obvious interpretation of that is to say, well, the real part is 3.14 and the imaginary part is the default value 0. However, implicit, they should be used sparingly because they can cause unexpected and undesirable effects. For example, our vector is defined so far as a constructor that takes an int. This implies that it defines a conversion from an int to a vector. Oh yeah, this is tricky here. When we assign 10 to a vector, that's going to make a vector of 10 doubles? Really? Is that what you intended? However, when we assign v to 20 to v, that assigns a new vector of 20 doubles to v. I mean, the way it currently works. And how about here? We got a function that takes a reference to a constant vector, and we're going to um, call the function f of 10. Calls f with a new vector of 10 doubles. That's not what you expected here, right? It seems we are getting more than we have bargained for. Unfortunately, it is simple. Fortunately, not unfortunately, it is simple to suppress this use of a constructor as an implicit conversion. A constructor defined explicit provides only the usual construction semantics and not the implicit conversions. So that's the use of the keyword explicit being used here, right? So we're not going to get any implicit constructor. So yeah, so here this will be an error, right? Because we're assigning 10 to a variable of type vector, and there's no implicit conversion from 10 to vector. Same thing here, right? So that's good. So we've avoided these confusing outcomes here. All right. And so here's a function that takes a reference to a constant vector. And again, that's going to be an error, right? So to avoid surprising conversions, we, and the standard, define vectors' single argument constructors to be explicit. It's a pity that constructors are not explicit by default. If in doubt, it's a pity, huh? Well, sounds like there's an argument there. If in doubt, make any constructors that can be invoked with a single argument explicit. Okay, 18.4.2, debugging constructors and destructors. 18.4.2, huh? What are we doing here? Okay, so this is this example that we were looking. So let's put that on the workbench. Oh, was that 18.5? I think it was. So currently, oh no, this is 18.5. So let's try excluding this. Okay, I'm going back to the code now, and I'm bringing in an existing item. I guess I'll try 18.4. I wish I remember what it was. Is it this one? No, this is back to the vector. 18.4.3. Nope, that's not it either. So it's not 4.2 and it's not 4.3. Let's keep. I know we saw this somewhere. Add existing item. 18. Well, 18.3.1. Ah, yes. Okay. So even though we're in section 18.4, the source code for 18.3 is what does this thing. All right. So let's close out these other ones, or exclude them from the project. All right. So here we've got a struct, and it says a simple test class. So a struct is essentially a class, right? The default value is the default status. Default status is public, right? So the variable val of type int is a public member variable. We've got a public member function called out that takes a reference to a constant string s and prints out this, which is the address of x, the struct x, and then it's going to print out the arrow operator, literal string indicating the arrow operator. All right, and then our string s, which is whatever the output is, followed by a colon, space, followed by the val, the private data member, followed by a new line. Okay. And then we have a constructor, right? We know it's a constructor because it has the same name as the struct. And what the constructor does is call this out function with the string x constructor, and the value. Oh, yeah. Shall we? Let's. I mean, they're trying to save lines, which I appreciate, but I think it's clearer if we expand that out, right? So then, here's another constructor. This constructor takes an int v and calls the constructor with an int, and right, same kind of thing, right? So basically, this is just to see how do things actually work. We're going to run this, and it'll tell us as it goes, and we may see some things that are surprising here. So let's get this working here. Here's the destructor. Now the destructor is also going to tell us what it's doing, right? It's going to. So this out function is basically just to print to the console, what the heck? What's going on? All right, and then we have a global variable, a global object of type X, initialized to 2. We have a global object of type X called copy. Now copy is blue, I guess, because, well, it's a function, right? Oh, sorry, we're declaring a function here, right? So this is not an object at all. Blah. So we have a function called copy, which returns a variable type X, takes a variable type X and just returns that. So the output is the same as the input. Copy 2 takes a variable type X called A, and creates a new variable of type X called AA, and uses the copy constructor, or the assignment operator, yeah, to assign the object of type X called A to the object of type X called AA, and then returns AA. Here we have a ref to X function, which takes a ref to X called A and returns a ref to X called A. Okay. Here we have a function called make, which takes an int I, construction an object of type X called A with that integer I, and allocates memory on the heap for a variable of type X, which is initialized to A. And here we have another struct definition called XX, and it's what? It's just got a couple of member variables of type X called A and B. All right, so then we declare a local variable, and I don't know, is it possible to see these two things side by side? The code that we're running and the output in the same window? Let me think about that. Well, let's run this and see what happens. Yeah, see, there's a lot going on here, right? So what's the first thing we see? Oh, well, we're not seeing anything, huh? Okay, Mario, I hear you. This is pretty rough going here, though. So yeah, So look at this is a private message to to Mario. Um, okay, look at 18 point. I think this is 3.1, isn't it? I think so. Oh, that's a 2. Let me go back here. Yeah, 18.3.1 source code. And make sense of so this is homework for everybody. Make sense out of this thing. Oh, he's gone. All right. Well, here, I will recommend this to everybody. Because as you can see, there's a lot going on, and it's not obvious what the hell. So where's this first line of code coming from? All right, and I don't know, can I? So I've got the output window, and this is, can I add a new window here? So this is the, so I've got a scene called output, and it's going to show the console output. Can I add a window capture to that? And I'm going to say that this is the source code for that, and say OK, and then go to this is, I think, here, right? Okay. So there it is, right on top, right? We don't want it to be right on top. We would like it to be over here, huh? And then we would like to scroll up here and say, okay, so the first thing we do is create a global variable, right? So where is this global? Oh, well, the first thing we do is yeah, so when this happens, we're creating a variable of type X called glob and initializing it to 2. And yet that doesn't produce any code. I mean, that doesn't produce any output, right? So which is the one that shows X of int? All right, it's up here, right? So if we're looking at, yeah. So here, yeah, so if I have, oh. So, yeah, notice that the value here is set to, can you see this? This value is set to 0 after we call out, right? Oh, sorry, this value is set to v here, right? After, so this is the constructor that takes an int, right? So our glob constructor takes an int 2, and the first thing it does is call this function, which is going to print what? Val, but the default value of val, we don't have one, right? It doesn't have a default value. So why is it 0? Well, that's probably just an accident of memory, right? So down here, when we call glob of 2, so let's reverse those. So where is it? Is it this one? So if I take this code here, I think I have to stop it, right? Oh, no, it's curious. Let's take that thing there and put it first, and then call out, right? So I'm going to close this, and first note that it says X of int 0, right? So now if I run this again, oh, yeah, so now it says X of int 2, right? Because so it seems odd that, you know, this x of int constructor here called the out before assigning the value, right? So we weren't, it wasn't obvious that that was glob because it said it was 0, right? And glob was initialized to 2. But that now, if we reverse those, we see, in fact, yeah, this is 2. All right, so where does this 4 come from? There's our next object. Well, and notice that this is the memory address, right, of our X object. It's all very abstract. But yeah, so when we call out, prints this, which is the address of the object which is calling out, right? Okay, so what's the next? The next output is x into 4. So I don't think there's not another global variable, right? So yeah, so we go down here and we see, yeah, so we declare another variable of type x called loc, and that is in a different memory location, an earlier memory location, it turns out. And it is, can I make this larger without, I think what I can do is, yeah, that makes that a little bit more easy to see. Oh, wrong window. So showing the source code first, I guess that's all right. Oh, we're just about out of time, huh? Okay. Well, so maybe we'll take up here next time. As when we're reading chapter 18, we're not very far through chapter 18, but it's pretty dense stuff. There's a lot going on here. Let me pause to ask if there's any questions about anything. So we're approaching the weekend for some of you. Okay. All right. I hope your other classes are going well, and that you've got enough of a challenge here to keep you interested. I don't know. It was sort of more interesting when we were doing the billiards. I know this is sort of meat and potato. Well, this is more broccoli, peas and broccoli. All right. Have a great weekend, Mark. Nice to see you here and in this virtual world. Okay. So I guess we'll call it there, and wish you a pleasant evening and a great weekend.